Good afternoon, everyone, and welcome to this September Green Seminar. Pleasure today to introduce Dr. Jennifer Hollingsworth, who is currently a Los Alamos National Laboratory Technical Staff member, Scientist 4 level, in the Center for Integrated Nanotechnologies at the Los Alamos National Laboratory. Jennifer received a BA in Chemistry from Grinnell College and a PhD in Inorganic Chemistry from Washington University, St. Louis, as a NASA Graduate Student Researchers Program Fellow under Professor William E. Bureau. Some of you may remember Bill Bureau because he came to Wynn in, I think it was March. March, he gave a seminar here. PhD work focused on synthetic routes to nanocrystalline and thin film 3.5 and 2.6 semiconductors, and following her graduate studies, she started at LANL as a director's postdoctoral fellow. And for her postdoctoral research, Dr. Hollingsworth was awarded the Distinguished Postdoctoral Performance Award in 2002, and since then she's received 2 other LANL awards for career development mentoring, program development, and she's also received the Chemistry Division Achievement Award. In CINT, the Center for Integrated Nanotechnologies, she's responsible for developing new approaches to the synthesis and assembly of semiconductor nanocrystal quantum dots and quantum wires, understanding structure-function relationships towards materials by design strategies, and creating and understanding unusual complex functional hybrid structures based on semiconductor-semiconductor and semiconductor-metal interactions. She oversees a team of chemists, inorganic biochemical materials, and the biotechnologists in support of these efforts. It maintains extensive collaborations both internally at LANL and externally in the areas of optical nanomaterials and nanomaterials for applications in energy and biosciences. She's the author of a number of journal articles and book chapters and has 4 patent applications. So please give a warm welcome to Jennifer Hollingsworth.
Thank you very much for the nice introduction and for inviting me to give this seminar. I've really enjoyed my day so far, and I look forward to meeting with even more folks tomorrow. So basically, this is a rather freewheeling talk. I plan to try to get across to you the full breadth of work that's going on in my laboratory over the past several years. And so I apologize if it drags on a bit, so we will cover both quantum dots and nanowires. Everything I do is from the solution phase. So that's the one thing that these have in common. They're also all semiconductor materials. And so my talk is basically 2 talks put together, or maybe 4 or 5 actually. But part 1 will focus on quantum dots, and part 2 will focus on nanowires. And so more specifically, with respect to part 1, the emphasis will be on 2 types of quantum dots that were developed in my laboratory. The first, the so-called giant nanocrystal quantum dot, or g-NQD. And the second, a new type of infrared emitter based on lead chalcogenide materials that are significantly more stable than your conventional near-infrared fluorophores. So first, with respect to the giant nanocrystal quantum dots, this is an area where we've really exploited nanomaterial or nanoscale heterostructuring to elicit extreme control over exciton-to-photon conversion pathways at this scale. And more on that as we go along. So we have novel nanoscale architectures. And then second, I'd like to demonstrate how we've been able to translate the nanoscale properties to the macro scale, or at least the micro scale. In this case, utilizing 2 light-emitting diode platforms as examples of nanomaterials integration towards functionality. And finally, I'll bring up the near-infrared case, just because I think that's a useful material that we haven't really capitalized upon as much as we could or can as yet. So in part 2, more specifically, the focus will be on how to make solution phase methodologies for growing nanowires more controlled so that we can achieve complex structures such as ternary compounds, but then also so that we can achieve heterostructuring of individual nanowires. And the example I show here is axially heterostructuring along the length of the wire, utilizing a new solution-based catalyzed technique that we call flow SLS. So to begin with, in terms of quantum dots, why do we care? And many of you probably are aware of this, but due to strong quantum confinement effects that come about at the nanoscale, in the case of semiconductor nanomaterials, we are able to elicit significant control over the optical properties of semiconductor nanomaterials by simply tuning the size of these systems. And so what I show here is the typical example of a cadmium selenide system. This is from Munji Buendi's lab from quite a few years ago now, where each vial contains the same material. Each vial contains cadmium selenide quantum dots in solution. But the solution on the left contains quantum dots that are on the order of 2 nanometers in diameter, whereas the vial on the right contains cadmium selenide quantum dots on the order of 5 nanometers in diameter. And so simply by tuning the size, we can modify the band gap due to quantum confinement effects and therefore achieve fluorescence colors that span the entire visible spectrum. And the same idea can be applied to many other semiconductor systems, including other 2,6 compounds, 3 5s, 4 6s like the lead chalcogenides and so forth, and achieve similar tunability in other spectral windows. And in addition, and this is significant, the emission that we achieve is narrow band and highly efficient. In these best case scenarios, quantum yields are approaching 100%, approaching unity, so 1 photon in, 1 photon out. And in addition, the absorption spectra are quasi-broadband that allows us to optically excite quantum dots very, very easily with a multitude of energies. And so they're very useful in that sense. And also the solution phase synthesis that's used is low cost, it's scalable, the particles are solution processable using polymers, sol gels, and so forth. And despite the fact that we're using, sort of low-tech methodologies to create these materials, we get a high-quality product out. The nanocrystals are single crystalline, and they exhibit low polydispersity when done correctly, on the order of plus or minus 4%, and that allows us to achieve these very narrow emission bands. And typically for cadmium selenide, for example, the full width half max is between 20 and 25 nanometers as prepared right out of the flask. I just want to point out, it becomes somewhat important a little bit later in terms of device applications, that all these materials that are grown in the flask comprise not just the inorganic core part, but also a monolayer of organic ligands that enables these particles to be suspended in solution for long periods of time and to be readily processed. But it also can cause problems, as we shall see. So the darker side of nanocrystal quantum dots. So I'm focusing here on 2 unfortunate attributes of quantum dots. One, their blinking behavior. At the single particle level, if you shine a laser at them and you observe their emission, you will see that the emission is not constant. The particles will emit light, but then turn off and then turn back on in a random fashion. And so for certain applications, for example, single particle tracking in biology, using these guys as single photon sources, for example, blinking behavior is obviously unwanted. And simply put, it's a non-radiative process that we could do without in many cases. In addition, quantum dots are characterized by very efficient non-radiative Auger recombination. And so I'll explain a little bit more about that in a moment. But in terms of fluorescence intermittency or blinking, under continuous illumination, it is thought that the quantum dot can become charged. This can also happen in a particular chemical environments, sort of redox active environments. And so it can be due to an Auger ionization process or other processes, but nevertheless, the quantum dot becomes charged, and then the charged quantum dot is susceptible to Auger recombination. So what we have now is an extra carrier, if you will. So if you generate with light another electron hole pair. The energy of recombination of that electron hole pair would ideally go into emitting a photon, but instead it's transferred to the third carrier, and it could be a hole, as I show here, or an electron. And that third carrier basically gets bumped up in energy and then decays and loses that energy non-radiatively as heat. And so therefore, a charged quantum dot in this traditional model of fluorescence intermittency is a dark quantum dot. And therefore, it has long been thought that blinking results from random cycle of charging and discharging events in the presence of an active Auger process. And so I show here the emission from a single quantum dot over time, and that you can see clearly the blinking process. The intensity is up, and then it's down, and so on. And this is a field of single particles emitting in a blinking fashion. Actually, more recently, we've developed a technique in SINT. It's a spectroelectrochemistry technique that is allowing us actually to controllably charge quantum dots and to at the same time observe the emission from the quantum dots and obtain their lifetimes, and to really more definitively assess the blinking process and the mechanism there. I won't go into that at all in detail, but suffice it to say, what we found is that blinking actually results from two different mechanisms. This traditional mechanism associated with charging in Auger, but also simply to hot electron capture to surface trap states that effectively short circuit the emission process as well. But in this case, the quantum dot does not become actually charged, and even though the quantum dot becomes dark, its lifetime does not change, and in contrast with the quantum dots up here. But anyway, this will be coming out shortly. It's in Press and Nature, and so it's kind of, you know, giving us a better understanding of what's going on with blinking towards the hope of creating more and more types of quantum dots that do not exhibit blinking. And so anyway, in general, non-radiative processes limit applications, and so many folks over a number of years have attempted to suppress blinking behavior. For quite a few years, the primary focus was on using organic ligands to suppress blinking, and these ligands were typically, they were so-called anti-blinking reagents. They were typically reducing agents that would serve to passivate surface trap states, for example, and if you applied these in a correct fashion, you could indeed suppress blinking, as shown here on the right. This bottom trace and this top green trace are examples of non-blinking behavior. However, it turns out that this type of approach was difficult to reproduce in the community, and it was found by us and others to be highly dependent on how you approached this process and how you stored your quantum dots. So more specifically, what we found out was that, for example, in the case of thiol molecules, that it turned out actually to be the thiolate anions that were able to initially passivate electron surface traps, and that indeed enhanced your optical properties. The PL efficiencies went up, and you actually had a short window of opportunity to actually suppress blinking. But unfortunately, when you applied additional thiolates, and it was hard to determine when that happened, you ended up introducing trap states, in this case hole traps. And so, and we use a combination of time-resolved PL and transient absorption methodologies to confirm that these so-called anti-blinking reagents actually serve two roles. One, initially to passivate traps, and then two, to actually introduce traps. And we published this several years ago in JAX. And so, in other words, it's very difficult to apply these organic compounds in just the right amount and in just the right time, and to hold it at the right pH and so on. A number of conditions were affecting what the results that you obtained. And so our ultimate conclusion, based on a number of optical studies and control studies, was that this approach really fell flat with respect to applications, in that you could not rely on it, and it was just too difficult to reproduce. And so we have therefore long sought an alternative to that approach. And in addition, the ligand-based approaches did nothing to address the flip side of blinking, that being the non-radiative Auger recombination process. This fundamental photophysical attribute of quantum dots was still not altered by putting ligands on the surface of the quantum dot. And Auger, as it turns out, is an important issue with respect to many potential applications, and I list some of these here. In terms of using quantum dots for lasing, when you have efficient Auger happening, you reduce your optical gain lifetimes, you reduce your optical gain bandwidth. You, in the case of photovoltaics and energy harvesting applications, you restrict the time that you have available to extract multiple excitons because they're being consumed by the Auger process. And in addition, if you want to generate single photons, it's hard to reliably extract single photons when Auger is active. And lastly, in the case of light-emitting diodes, for example, for solid-state lighting applications, in a standard electrically pumped or driven light-emitting diode, the light-emitting material can easily become charged. Extra charges can build up, either electron or hole carriers. And so in that case, Auger will really diminish the efficiencies that you can obtain from your light-emitting device if the active emitter is a quantum dot. And so for all of these reasons, we really wanted to find an alternative approach that would allow us to simultaneously address the simple issue of blinking as it related to surface effects, but then the more complex or interesting issue perhaps of Auger recombination, the more fundamental issue. And so we knew organic shell, if you will, approaches were not adequate to the task. And so we decided to focus on inorganic shelling. And it was already known, very well known in the quantum dot community, that if you grew a thin shell of a higher band gap semiconductor onto your quantum dot, that you could easily enhance the ensemble level properties. Your photoluminescence efficiencies increased. And yet, none of those systems exhibited anything different with respect to Auger, and nor anything different with respect to blinking. And so, but we thought we could tweak this a little bit and actually do a couple of things. Number one, we thought that if you created a very, very thick shell, that you could effectively isolate the excitonic wave function that you generate under optical excitation, for example. And therefore minimize any surface or surface trap related behavior. And in addition, render optical processes such as blinking or even photo bleaching and the ensemble level property of quantum yield independent of the chemical environment of the quantum dot. And even though a thin shell system was definitely shown to go in the right direction, it just hadn't been taken far enough. But in a more subtle area, we hoped that if we did this shelling procedure correctly, that maybe through especially electronic structure manipulation, we would also be able to address the issue of Auger. And so Auger can be influenced by a number of factors. First is the volume effect. If you decrease Coulomb coupling by increasing the size of your nanostructure, that itself will reduce Auger recombination. If you reduce electron-hole overlap, and that can be done by modifying the electronic structure of a quantum dot heterostructure. For example, what I show here is the case of a so-called quasi-type 2 electronic structure where we're able to achieve partial electron-hole separation by energetically confining the whole wave function to the core of the quantum dot, whereas the electronic wave function is actually able to spread out into the shell because the difference in energy here between the conduction bands of the core and the conduction band of the shell are relatively close together, and therefore you get this partial spatial separation of the two carriers, and that itself can reduce Auger efficiencies. And then lastly, theoretically it was shown by Sasha Efros some years ago that potentially if you blurred the interface between the core of the quantum dot and its shell, such as like by forming an alloy, for example, that by smoothing the interfacial confinement potential, that itself could also additionally impact Auger. And so, we sought basically a system that would allow us to achieve this combination of beneficial effects. And we also had a model from the vapor phase community. So if you look at epitaxial quantum dots grown by MBE, if those are prepared properly, you actually can exhibit non-blinking behavior and also suppression of Auger recombination. And so effectively what we were attempting to do was to take an epitaxial quantum dot and make it in the flask at low temperature and using simple, cheap methodologies. So we had to find a method of growth that would allow us to achieve or retain single crystallinity, retain minimal defects in our quantum dot, even when we were growing many, many, many monolayers of shell material. And so at that time, we looked in the literature and found that the best approach to growing shells on quantum dots was the so-called successive ionic layer adsorption and reaction, or SILAR technique, which allows us to apply monolayer by monolayer, or actually half monolayer by monolayer, of the shell material. And we were able to do this many, many times. We actually significantly modified this procedure ultimately to create the control we needed to make sure we retain the high crystalline quality even at the very thick shells. But we published this a couple of years ago now in JAX, and then actually we're followed by a group out of France. A couple months later, we had the same ideas apparently, and so some interesting work, and then since then published again some more detail here. But anyway, our systems tend to focus on shells that are very, very thick, up to about 20 monolayers of shell material. In this case, CAD sulfide deposited on the CAD selenide gives us that quasi-type 2 electronic structure. And just as a visual for the why we call these things giant, we're typically used to working with quantum dots on this size range, 3 to 4 nanometers. And after we grow, and it's on the same scale, these two are, and after we grow, say, 19 monolayers of shell at this point, our particles are now between, say, 12 and 20 nanometers, depending on how many shells we grow. And so, in some sense, they're giant, but that wasn't meant to scare away the biologists who like to have things small. So I think they're still small enough for practical use in many single molecule applications. Anyways, high-res image on the right shows the nice crystallinity, the faceting that we achieve that reflects the underlying hexagonal crystal structure of the system. And so we made these guys big, so what? Do they work? And our first inkling that they worked is shown here. This is from the first paper. And we were directly comparing the so-called giant quantum dots with the commercial core shell quantum dots that are very nice materials. They have very, very high efficiencies in terms of ensemble quantum yields. But nevertheless, they exhibit typical blinking behavior. This is a single particle time trace for PL intensity. And I want to also point out that on a conventional core shell system, not only are the particles turning on and off and blinking, but you can see that the intensity is declining over time. And that's an indication of photobleaching. So conventional quantum dots under continuous excitation photobleach. Whereas the giant quantum dots we found are not only exhibiting the suppressed blinking behavior, but are non-photobleaching. And this is all very much a function of the shell thickness. We seem to have some thresholding. These are the first results. In this case, about 20-some% of the ensemble of quantum dots were exhibiting completely non-blinking behavior. Since then, we've increased that percentage dramatically, and I'll show you that result in a second. But I want to point out, too, in contrast to the other couple of reports in the literature looking at thick shell effects, we really kind of torture our dots. We hit them with a laser for over an hour, about an hour, when we're doing these blinking studies. So I think, more typically you'll find in the literature blinking results that go on for a couple of minutes. And so I feel quite confident that we've really achieved something unique here because of how harshly we can treat the particles, and yet they still exhibit these unique behavior. Anyway, and then so I mentioned the shelling is significant in terms of the number of shells required to achieve the non-blinking behavior. So again, here we're looking at the fraction of an ensemble of quantum dots that are on for more than 99% of the time, that time being about an hour. And so therefore, this is the non-blinking fraction. And you can see that the fraction that maintains its non-blinking behavior is highest for the thicker shell system. So the 15 cadmium sulfide monolayers, for example, as opposed to 5 and 7, and even actually 7 and 10. And if you look at the 5 monolayers of cad sulfide, there's nothing that's still non-blinking after that observation time. So really the shell thickness makes a big difference. And then more recently, we were able to achieve through optimization of our reaction conditions, and this is very complex. We've got a lot of parameters to consider. Even reactant order of addition actually has played a significant role, believe it or not. And anyway, now we can achieve ensemble properties such that more than 80% of the quantum dots are non-blinking. So that's very exciting. And unexpected synthetic knobs that we now have that we can tweak. It turns out that your starting core diameter actually makes a big difference. And so if we have a larger starting core or cadmium selenide core diameter, we need fewer shell monolayers to achieve equivalent blinking behavior or blinking suppression as we do for smaller diameter cores. And this is it appears to be a volume effect. So effectively you start with a bigger core, you need fewer shells, you have the same volume as a small core and many shells. But it's not strictly correlated to that, so we're still trying to understand what's going on there. And then so that's all about blinking, which could conceivably be a surface charge effect only because we have a thick shell. As I mentioned, we're protecting the excitonic wave function and so on. So do we have evidence to suggest that we've done something more than that? And specifically with respect to Auger recombination and suppression of Auger. And indeed we do. This is collaborative work done with a group out of chemistry division. I'm actually now in materials physics and applications. And they use pump intensity dependent time resolved PL to demonstrate that, at least indirectly, that Auger is suppressed. And so what we see here on the left are time traces as a function of pump fluence for conventional quantum dots. And you see that standard, PL decay from sort of biexciton or multi-exciton states is very, very rapid due to Auger recombination processes, whereas single exciton decay is, of course, much slower. It's not affected by Auger. And so this rapid decay of multi-excitonic states is an indicator that Auger is active. And you can actually use this data to calculate biexciton lifetimes. So how long can a biexciton live? And that's just 2 excitons, sorry, in a quantum dot. And it's only 0.2 nanoseconds in the case of conventional quantum dots. You do the same thing for giant dots, and you find that this multi-excitonic region actually is highly extended in time. And so now we calculate biexciton lifetimes that are 10 nanoseconds long. So they're actually almost equivalent to our single exciton emission lifetimes. And so clearly something is changing. And then also with my closest collaborator, Han Toon, who's in SINT, we've also demonstrated that the giant quantum dots actually can efficiently emit from charged states, from biexcitons and multi-exciton states, and this was published in Nanoletters in 2010. And so he uses a low temperature photoluminescence method, and what he sees is that when you pump a conventional quantum dot very, very hard, as you're increasing the pump intensity, the pump fluence, your intensity increases, but only to a point. And then those quantum dots will photobleach and die and never come back, and you've destroyed them. And also, you only see a single emission pink, and maybe it's LO phonon reflection over here, even at high pump intensities. Whereas in the case of giant quantum dots, as you keep increasing the pump fluence, you start introducing new states that are emitting. And so in this case, I'm showing charged exciton and charged biexciton states. We also see much higher order multi-exciton emission, depending on whether we're pumping CW or pulsed. But anyway, so clearly something new in terms of the fundamental photophysics is happening in these systems. And so that's exciting. And now as a chemist, of course, we'd like to say that we just didn't get lucky. You know, we'd like to be able to say that we can control this, we understand this well enough that we can go ahead and translate what we've learned from the CAD selenide, CAD sulfide system to another system. And so we've been focusing quite a bit on the indium phosphide-based systems, initially with the idea that indium phosphide is more benign compared to a cadmium selenide core material, and so biologists will like it better and so on. But of course, the system that's working best right now happens to have a cadmium sulfide shell. So whatever, the physics is still interesting. So this is the first extension of the, quote, you know, giant concept to a new system. And you can see we are, like the other system, growing thick shells in a nice fashion. They're not quite as pretty yet, but pretty good. And we have very tantalizing new evidence that these systems are also exhibiting unusual behavior. In this case, we're looking at blinking effects. And so even at 4 monolayers of cadmium sulfide, we have this sort of funky behavior where we're still blinking, but the off times are very, very short and kind of characteristic almost. So this would suggest that this system might drive towards a single sort of off time or state. Whereas in cadmium selenide-based systems, this type of thing was not observed until the giant dot scenario. And so in the cadmium selenide-based systems, what you typically see is that there's no characteristic off time. So that itself is interesting, but then when we go ahead and grow the shell thicker, we see clearly evidence of suppressed blinking. And I know I harped on the 1 hour thing. Because these are actually emitting in the near infrared. This is hard work to get this data. And so what we're waiting for is to find our best sample, and then I'm going to make the poor postdoc take it out for an hour so we can look at photobleaching effects. But we can't do that as we go. So, but that's kind of exciting. And we like indium phosphide in general because if we tweak the composition of the shell from a zinc sulfide to zinc selenide to CAD sulfide, CAD selenide, we can actually tune through as a function of the core size, but also the shell thickness. We can tune through all 3 types of electronic structures from type 1, we have full confinement of the electron hole pair, through the quasi-type 2 stage, and occasionally in some of these systems to a fully type 2 scenario where we get full spatial separation between the carriers. So we've actually are developing new syntheses. Prior to our work, really the zinc sulfide indium phosphide system was the only one known, maybe 1 paper on zinc selenide. And so all of this is a new material space, and so pretty exciting, we think. And just to give you an idea, with the cadmium selenide containing shells, we're able to tune emission energy with its thickness. So as we increase the number of cadmium sulfide or cadmium selenide shells, and these are all the red guys here, you can see that our starting emission, you know, and this is in the visible, but very, very quickly as we increase the number of monolayers, we're pushing out into the near infrared. And this along with lifetime studies that we've done, is clearly an indication that we've created from a quasi-type 2 to a truly type 2 system. And it's these orange guys that are giving us the non-blinking behavior so far. We haven't looked at the CAD selenide-based ones, but and anyway, then with the zinc, we can actually keep in the visible region, which for certain applications is nice. But okay, so that was the first part of part 1. Now I just would like to convince you that we can attempt at least to translate our nanoscale photonic control to the macro scale. And so with the giant dot system, we're clearly showing that we have access now to new exciton to photon pathways. And that's exhibited by our ability to emit efficiently the multi-exciton from multi-exciton states. And so now, are these useful in actual device scenarios? And so the aim here, of course, as always, is to try to combine the best of what's currently the state of the art. So, you know, there's the state of the art in LEDs with respect to inorganic nitride-based technologies, where we've got high efficiencies, high stabilities, and so forth, but relatively higher costs, but try to couple those benefits with lower cost solution based systems and that would have the processability of your organic or polymer LEDs, for example. And so quantum dots in principle should be able to combine all of these attributes. Of course, I don't think anyone's there yet, but okay, so the current status as we know it in terms of NQD LEDs is that if you combine inorganic, quantum dots with conventional organic LED materials, you can actually create devices that have EQEs in the order of 2 to 3%. And actually, I just spoke recently with Professor Bolovic at MIT. He claimed a 10%, although he didn't have a reference. So that would be great if that were the case, but I'd like to say, looking forward to seeing it. So we're communicating with him about that. But in the meantime, it's still sitting at 2 to 3%. And actually, these systems benefit from indirect or energy transfer pumping from these organics that themselves emit light. And then the quantum dots are very good antenna. So that's really the reason these devices are functioning as well as they are. In the case of sort of all inorganic LEDs based on quantum dots, where you're directly charging, injecting charge into the emitting quantum dot layer, EQEs, or external quantum efficiencies, are hovering at between 0.1 and 0.2%. So not that great. And the most recent, these are from these 09 and 08 Nature Photonics and ACS Nano papers. This is all mostly coming out of Bowendi and Bolovic's collaboration at MIT. So anyway, they're kind of an obvious question. So why are the NQD LEDs performing relatively poorly to date with all their promise? And so we and others point to two key deficiencies of the quantum dot active layer. The first being that, as I've already alluded to, quantum dot optical properties in the case of conventional nanoparticles depend on their passivating molecular organic ligand layer. And one problem is that when you process the quantum dots into the solid state, these organic ligands can become damaged. They can kind of separate from the quantum dot surface, or actually more importantly, under optical excitation, they can become damaged, oxidized, and so forth. Anyway, so anything that can deleteriously affect the organic ligands themselves or their interaction with the quantum dot surface can suppress emission from the quantum dots. And in addition, these ligands can provide an insulating barrier to charge transport. So if you want to build a device that has multiple layers of quantum dots, then you're dealing not just with the emitting core, but with this insulating organic material. And you may actually affect differently the different carriers and create an electron hole imbalance in the quantum dot. So anyway, ligands are generally considered bad for LED applications. And in addition, we've already talked about the Auger recombination process. So again, in LEDs, the emitting material can become charged, and by Auger processes, a quantum dot will then become dark. And so we've got these two deficiencies of a conventional quantum dot system. And so, of course, we view the giant dots as somewhat transformational in this area. We've actually demonstrated that their emission properties are generally insensitive to surface effects, so we can actually put these guys in the solid state. We can replace their ligands with something that's volatile. We can pump on them and heat them up, and we find that the emission from the giant dot stays the same, whereas we compare that to a conventional core shell quantum dot, and after 5 minutes of annealing, the emission from the conventional system is gone. So that shows that potentially one could actually remove ligands in the giant dot case and still have activity. In addition, of course, we can suppress Auger recombination. And I didn't mention this before, but in the giant dot case, we have a large effective Stokes shift. So you minimize self-reabsorption in your devices. And so a conventional quantum dot, the energy separation between the absorption onset is very, very close to the emission peak. In the giant dots, because the primary absorption comes from the shell, which is significantly bluer than the emission from the red core. So we have a large effective Stokes shift. And this actually plays a role when you use these guys as phosphors, and I'll get to that in a moment. We are still able to retain a reasonably narrow band, although not as good as a conventional quantum dot. The giant quantum dots are typically 40 to 45 nanometer full width half max. So So very, very simple device structure we've used as a test bed to compare giant quantum dots with conventional quantum dots. This was so simple that Professor Bolovic couldn't believe it worked, but it does. We put our sandwich our giant quantum dot layer. In this case, it's actually only a monolayer between a cathode and an anode. And I actually want to run, in the interest of time, we can go back over this if someone wants to see this in more detail. But anyway, we put these hole and electron blocking layers in there to kind of control how carriers are injected into the quantum dot layer. We had to play around with the thicknesses of the lithium fluoride and the p-PSS and so on to minimally optimize the structure. We're not engineers, so it's nothing compared to what I think a lot of you guys can do. But anyway, it works. And so we were able to obtain LED performance from our giant dots. In this case, the 16 monolayer CAD sulfide system that's equivalent and even a little bit better than the state-of-the-art all inorganic devices that are in the literature currently. We have a maximum luminance of 2,000 candela per meter squared. Our EL turn-on is actually fairly low. It's 3 volts. And our maximum EQ is 0.16, and as I mentioned, literature is between 0.1 and 0.2. So considering that we have a much simpler device design, we certainly aren't optimized. This was a pretty good result. And then skip this. If color purity is obviously good because nothing else is emitting. It's just the dots. So it's narrow band, red emission. That's that. We actually do see a little blue region popping up under increased current or bias, and that's likely because of the multiexciton or emission. But anyway, so comparing our devices with the literature, as I mentioned, we're already right there with the best that's out there without even putting in, creating a much fancier LED design. But importantly, our EL turn-on voltage is actually lower than what's out there. We're at 3 compared to 4 to 6, so that was pretty good. And if you compare to, if you go way back in the literature to 2003, a similar device design was demonstrated back then. So it's a very simple structure, just like ours. And their EQs are 0.002%. And so we're a little bit better than that. So, and again, higher turn-on voltages. And so if we look specifically at the effective shell thickness, we find something somewhat interesting. The dirty secret of giant quantum dots is that you increase the shell thickness, the quantum yields actually are going down. And so the best we've been able to achieve so far is about 50% quantum yield in solution, ensemble quantum yield for the very, very thick shell systems. And that compares fairly poorly to the thinner shell systems that give us quantum yields about 80%. So anyway, we've got, although we're not showing our best here. And so what we have here is solution phase properties are actually declining to some extent for ensemble properties in the case of the thick shell systems. In addition, because our giant dots are big compared to the thinner shell counterparts, if you create a monolayer of either material, you actually have effectively fewer emitters in the giant dot monolayer compared to the thin shell monolayer. And so now we've got, in the case of a solid state monolayer, fewer emitters, and in the solution phase, they were poorer emitters. And so, but what do we find as we increase shell thickness? Instead, we find that our EQEs actually go up significantly, as well as our maximum brightness as we increase shell thickness. So our solution phase properties are not corresponding very well to our solid state properties. And so why is this happening? We appear to have more active emitters in the devices as opposed to the solution phase, or we've enhanced the per particle brightness. We're not sure yet. But how could any of this be happening? Again, we look to the fact that if there are bad ligand effects affecting the thin shell systems, those effects are suppressed in our thick shell system. Auger, of course, is also suppressed. And lastly, quantum dot to quantum dot energy transfer, which in a dense film of dots can actually kill your PL. You tend to transfer from high energy dots to lower energy dots. And also there's actually a paper out recently that suggests that the transfer is preferentially to trap-ridden dots. And so that process itself can kill you in the solid state in the case of quantum dots. And anyway, the thick shell systems have advantages in all 3 cases here. This is some of our energy transfer studies where we definitely showed that energy transfer is effectively turned off in the thick shell systems. So do we have an issue in terms of the thick shell impeding charge injection? The answer seems to be no. Our turn-on voltage is about the same all the way across the series, so that's good news there. And then I think I'll fly through this. So we've also demonstrated that giant quantum dots can be used as phosphors, and here we're taking advantage of stability and Stokes shifted emission. I think I'll skip this. Yeah, and so this is a demonstration of why a bigger Stokes shift is better. And so here are data of PL intensity versus optical density, where optical density can be viewed as correlating with the concentration of quantum dots in your system. So in this case, we're using quantum dots as phosphors. We're optically exciting them. We have an EL phosphor device, and then we've just slapped a layer of quantum dots, and the quantum dots in this case are embedded in a polymer on the other side of a glass slide. And we electrically excite the blue phosphor. It emits blue. The quantum dots down convert to the red. And what we're now looking at here is the PL intensity of the red emission. In the case of a core-only phosphor material, you can keep increasing the number or the density or the concentration of quantum dots in your slab of quantum dot plastic in your device. And initially, you increase the intensity that you're getting out. But actually, as you keep increasing the concentration of the dots, you get self-reabsorption effects. So the dots reabsorb their own light. In the case of giant dots, we increase to the same concentration, and so normalize at the same wavelength. And we see that we're not having those problems. So that's a good news for use of giant dots as phosphors. And we also find that stability, we're looking at about 50 to 60 hours, of the thicker shell systems is significantly improved compared to the thinner shell or the core-only systems. This initial drop actually has to do with the EL phosphor and not with the dots at all. So, okay, so conclusions in terms of giant dots. I think we've demonstrated that we've made significant progress towards controlling exciton-to-photon conversion pathways at the single particle level, and that there's now clear opportunities for enhancing the efficiencies and the stabilities in NQD-based LEDs. So that's good. And then very, very quickly on the infrared case, this is a little bit older work, but I think still relevant. So infrared emission is important for a number of applications, from telecom, tunable IR lasers, photodetectors or solar cells, bioimaging. The tissue transparency in the infrared is significantly better than in the blue or green visible. So a number of reasons why you might want fluorophores that emit effectively, efficiently, and stably with stability in the infrared. And so the case here is that of lead selenide quantum dots. When we entered this arena, there were nice preps out there for high efficiency, high quantum yield lead selenide quantum dots that emitted in the 1.2 to 2 micron range. We were able to develop new methodologies to grow larger and better particles that extended our ability to emit all the way out close to 4 microns. So really taking advantage of the entire of the bulk band gap of lead selenide, actually. So lead selenide is a nice material in that it has a bulk band gap around 4.7 microns and a very large Bohr radius. So that means that you don't have to go to very, very small sizes to achieve high quantum or strong quantum confinement effects. So you can get a lot of spectral tuning even at fairly large sizes. So it's a nice material to work with. Our efficiencies, 3.5 microns were only 5.5%, but frankly, that's pretty good if you think about the dye, IR26, which is your most common near IR dye, molecular dye. It has a quantum yield of 0.5%, but that's like at 1.1 microns, not at 3.5. There's nothing that's like that. So this is quite unusual in that respect. So significant tunability, I'm going to skip this. We were interested for various reasons in using these guys as optical labels in the near IR and the mid IR. And indeed, you can clearly distinguish the emission from the quantum dots from background heat by doing simple time gating techniques. And so what wasn't working with lead selenide was stability. They tended to readily oxidize. We demonstrated using some variable energy synchrotron radiation photoelectron spectroscopy that the seleniums on the surface were clearly oxidized over time and diminishing our photoluminescence and also caused significant blue shifting over time. Anyway, so of course everyone wants an inorganic shell approach. You can improve your stability and your efficiencies and so on. The problem with lead selenide, we've got high lability of the lead and the chalcogenide atoms. And so when you try to apply conventional shell growth techniques that rely on relatively high temperatures, the lead selenides tend to aggregate and grow and so forth. And so traditional methods would not work. And so we use a new approach where we utilize a cation exchange to create a cadmium, in this case cadmium selenide shell over lead selenide. So essentially we introduced cadmium ions to a solution of the lead selenide under controlled conditions, and this resulted in the some of the cadmium replacing some of the near surface lead ions, and we actually were able to replace between 5 to 70% of the lead with cadmium. The selenium stays, and so you extrude lead and you put in cadmium, and so then you effectively shrink the lead selenide core and replace it with a cadmium selenide shell. And then once you do this, these particles become more like cad selenide than lead selenide, and you can grow, by standard methods, other shells on top of that, like zinc sulfide, and make them nominally more biocompatible. Anyway, so this, of course, process results in blue shifting, but then you stabilize the particle with the shell, and the emission intensity enhances significantly. We did TEM, XRD to demonstrate the shelling. But clearly the stability is greatly enhanced. These are core shell, lead selenide, cad selenide quantum dots stored under ambient conditions, so relatively minimal quantum yield issues and no spectral blue shifting, whereas even if you store untreated quantum dots in a freezer in the dark, they will be down to 0 efficiency within a month. So that was a nice result. Okay, so I'll go on to part 2 of the talk, and this is much shorter than part 1, so no worries. Anyway, so controlled, just to remind you, we're switching to nanowires now. Controlled solution phase synthesis of complex semiconductor nanowires. And so in the first part of the outline, the first case here, what I mean by complex is compositionally complex, in that we've developed a method to grow a truly ternary compound, copper indium diselenide. And your interest in nanowires in general is often in the area of energy harvesting. People in my field use quantum dots and their assemblies as energy harvesting agents, as I show here on the left, but you rely on carrier hopping, which is a fairly inefficient process to collect your charge. So we like the idea of a semiconductor nanowire due to its anisotropy. It allows us potentially to direct carriers in a certain direction and out of the device. So nominally that's sort of the excuse for studying these things. It's also interesting just to sort of understand how you what things happen, what happens to the chemistry and physics as you go from 0D to 1D. But anyway, and so Bill Burrow was here not that long ago, and he is the father of solution liquid solid growth. And so in this work, I largely follow that methodology. It's similar to vapor liquid solid growth in terms of mechanism. In both cases, you have a molten metal flux into which you incorporate precursor compounds, and then upon supersaturation, your semiconductor material nucleates and then begins to grow, or continues to grow. And we do the same thing in SLS, except for in SLS, things are happening in solution, and typically at lower temperature, and we also get significantly faster growth rates, so many microns are wires are popping out in seconds, and the wires are freestanding. And then so anyway, we use this in our lab in general to grow a number of systems. It gives you great flexibility, just like the quantum dot approach to synthesis. We've grown lead chalcogenide-based nanowires, cad telluride nanowires. This is actually a bundle of, these guys like to self-align. So anyway, so what's new though from our lab? We actually developed a new synthesis for copper indium biselenide with the idea of moving towards CIGS type systems that are useful for photovoltaics. And initially we utilized a multiple source precursor route, so separate cadmium, indium, and selenium precursor materials. And we found that you had to be very, very careful about how you control the ligands, the temperature, et cetera, et cetera. And otherwise, sometimes you got very, very ugly stuff. Sometimes you got particles, and only in a small window of opportunity to get relatively decent wires, but never were these terribly stoichiometric. So anyway, we then switched to a single source precursor route. This is actually a precursor that's commonly used in CVD synthesis of thin films, for example, but we can put it in solution, and we effectively have pre-assembled copper, selenium, indium bonds, and this indeed allows to create phase pure material that was nearly stoichiometric and minimal between nanowire variability, so fairly constant results. They're not terribly pretty, but not too bad, and a consistent incorporation of all three elements. So anyway, that was quick. Okay, and last but not least, newer work in my lab. We are trying to make SLS better by making it more controlled. And so as I mentioned, traditional SLS is one pot growth. Similar to quantum dot growth, you heat up a flask of solvent. Some of it's coordinating, some of it's non-coordinating solvent. You, in this case, add a slurry of nanoparticles, often bismuth or tin, something low melting. They suspend and are molten, and then you inject your precursors, and then particle growth happens typically very, very rapidly in not a terribly controlled fashion. And so what we sought to do then was to actually make SLS a little bit more like VLS, or more like vapor liquid solid growth, where vapor liquid solid growth has the advantages of being able to introduce precursors in a more controlled fashion to your molten catalyst flux, and to remove byproducts, because it's a flow-based technique. You're flowing in gaseous precursors, they're reacting, and then byproducts are disappearing. A new reactant can come in. And so the VLS world is able to more easily create axial heterostructures, for example. So you can pass in one precursor, create a segment of one composition, flow it out, flow in another precursor, create the next segment, and so on and so forth. And so we just really haven't been able to have that level of control in the SLS approach. And so, so we sought effectively to do two things. Allow us to slow down the growth process, to be able to really study kinetics in this system, get some fundamental understanding of the growth process, and then also to create an easier way to axially heterostructure the nanowires. And so, okay, so a couple of examples in the literature in terms of growing axial heterostructures. This is at a Parks group at Harvard, where they took a bismuth-coated substrate, put it in a flask, added precursor, washed the substrate off, put in another flask, added the next precursor, and they could do this a couple of times and get these cad sulfide, cad selenide, cad sulfide heterostructures. But it's a multi-step, fairly tedious process, and it's clearly not going to get you all that far in terms of the number of segments. And this is at a Bill's lab, actually, where they demonstrated zinc selenide, zinc telluride, axially heterostructured nanowires. These were grown in a flask, and he did it a couple different ways. One, he just added sequentially the different precursors, and they tended to get a nice kind of alloyed interface. If he took the first segment out of the solution, washed it up, put it back into another growth solution, added the next precursor, he could get a fairly clean interface. But again, it's a tedious process of washing, putting it back in a new flask, and blah, blah, blah. And so, clearly we didn't think that was too ideal. And this, so So we developed a flow-based approach using a microfluidic flow reactor and a custom fluidic chip. We worked with a company to develop this chip. And so the chip has this sort of fairly large working area, 1 by 2 centimeters. Actually, the active area is quite a bit smaller than that. But anyway, the special thing about this chip is it allows us to open it up, put in a substrate that has our catalyst particles on it, close it, seal it, do the flow chemistry, high temperature, 330 degrees C typically, liquid phase, and without leaking sometimes. That's actually the biggest issue here. And then do the reaction, then shut everything down, and then open it back up, pull out our substrate, do the characterization, and reuse it over and over and over again. And so that part of it's actually working very, very well. And so, and microfluidic systems are known for their controlled flow. We have laminar flow, tunable flow rates, resonance times, reaction temperatures. So ideal conditions for more controlled growth, but also because it's a flow-based technique, the ability to alternate precursor supply, and therefore we hoped to facilitate axial heterostructuring. And so initially we just did some basic studies on the growth processes that was, and as a function of temperature, as a function in this case of bismuth film thickness. And in this case we were not putting in individual particles in a substrate. We actually supplied a film of bismuth that melted under the growth conditions and formed droplets on the substrate. So fairly random, but it was the easiest way to go. And so as a function of bismuth thickness, you can clearly see an effect on the diameter of the particles or of the wires formed. Temperature, small increases in temperature dramatically increase the length of the wires we achieved, and also you can see here the diameter was greatly influenced by the thickness of that bismuth, going from 2 to 5 to 10 nanometer thick films. Our wires changed from diameter 16 to close to 40. Time was a big player. You go from 10 minutes to 30 minutes of reaction time, and the wires are over a micron. But again, this is way slower than what was happening in the flask. In the flask, in a matter of seconds, you get tens of microns long wires. So this is a very different thing going on. And then if we do, like my former postdoc Raiwan Lao Sharanshuk did, and do a very, very careful analysis of the relationship between length and diameter and growth rates, we found a clear indication of the Gibbs-Thompson effect for the first time in the solution-grown system. So this is commonly observed in VLS-grown nanowires, and this is the first observation in the SLS world of diameter-dependent growth rates. And so, what you find is that for very much smaller diameters, your growth rates are suppressed due to this effect. And so the other thing to point out here is that the flow SLS growth rates that we calculate are very, very small compared to traditional SLS. So less than a nanometer per second, versus tens to hundreds of nanometers per second. And so we've achieved what we wanted to do in terms of more controlled growth, and we've obtained a new ability to look at kinetics in the SLS system. And so that was all good. Now can we, oops, I changed the title. So did we, can we make axial heterostructures, which is our other goal? And indeed, we can. And I'm only showing some of the data, but basically we find that our ability to heterostructure in this way is highly dependent on the growth conditions, the thickness of that bismuth layer, the size of the diameter of the particles, and so on, but also on temperature. A small change of 30 degrees, and what we find is we're not able to achieve clean AB-AB structures. We actually never fully get rid of the zinc selenide, for example, in the wires. And so we have a clean system and an alloy and a clean system and an alloy. In the contrast, with a higher temperature and faster, we bump up the growth rate of the zinc selenide, we're actually able to achieve nice sharp interfaces and clean zinc selenide, Cad selenide, zinc selenide, Cad selenide interfaces or heterostructuring. And then last but not least, so far we've been able to demonstrate up to 8 segments by this approach. And so that's, we find very exciting. So it's toward toward, not there, unlimited axial heterostructuring. So conclusions with the wires. So the first demonstration of SLS applied to a truly ternary semiconductor material. We've established the flow SLS technique as a better way to control solution phase growth. First observation of diameter-dependent growth rates. Demonstrated the capability of the flow cell for complex heterostructuring, and so on. And what I didn't show is we also have solution phase techniques to actually fabricate in situ hybrid nanowires. We have semiconductors growing directly off of a metal rod or metal wire. So the idea there is to have established in situ contacts between metals and semiconductors, which, you know, for solution-grown semiconductor materials is a big deal because everything we grow in solution is coated with this fatty, you know, layer of organic goop that makes them somewhat hard to contact. Of course, now we have the fatty goop all over the metal too, but that's something we have to solve. But the interface is clean. We have nice high-res imaging that shows that. Okay, so some acknowledgments. I'm missing a lot of folks here. This from a different talk, actually. This is the g-NQD team. And so it's mostly Yagna and Allison, and then Janardhan's working on the devices. Raliwan and Kumar have been key to the nanowire work. Raliwan just completed her postdoc and is now a staff scientist at a national lab in Thailand, which is very nice. And so that's it. And then I work a lot with various spectroscopists, especially Han Toon and his team of postdocs. And our funding is varied, some DOE, some internal, but also NIH and NIGMS in the area of single particle tracking work that I didn't show at all, actually. So, and last but not least, we're looking for good students to want to be postdocs. So, thank you for your time.
I'm sure that Jennifer will be prepared to answer questions if there are any.
Yeah. Very interesting, obviously quite productive. Question regarding type 2 electronic structures. And, I mean, I can see why the cadmium selenide valence band would be higher. And that's obviously what you want. But if you add more and more cadmium sulfide shells, wouldn't the valence band then go up? Because you're losing the quantum effect?
To a point, but we've also shown that actually there isn't, so it's actually quasi-type 2, actually. So we don't have actual transfer of carrier into the shell. There's just this partial, you know, electronic spreading into the shell. What we've also shown in some other studies, though, is that the separation is only for the first, and I forget how many, 4 or 5 monolayers. That actually at some point you do have still actual confinement. So the shell is still confining both carriers at a certain distance. So it's actually a little bit more subtle than I'm showing here. But
because you're blinking suppression
yeah.
Had the exception when you had the largest number of layers. When you added 19 layers, it already went down again.
It went down again, but that could be due more to strain effect and adding defects. I mean, yeah. My guess is it's more to do with that. Yeah.
Can I?
Oh,
more short follow up.
yeah.
Would you actually measure those states where they are with respect to energy, or calculate that?
So calculating, we work with some theorists at Los Alamos. Yeah, measuring, actually, we just started some electrochemistry work in my lab. Yagna, who is one of the giant quantum dot ladies there, is actually looking at trying to really pinpoint for real, you know, where the valence bands and conduction bands are. And actually, what's odd, so in terms of as a function of core size, you know, typically everyone says that it's the conduction band in the CAD selenide materials that moves around, you know, when you go from bigger size to smaller size, and that the heavy hole, you know, keeps things kind of stuck in the valence band. But we're doing some, I don't know, some of our measurements so far are actually showing the exact opposite. We changed the size from big to small, and the conduction band is staying, and the valence band is moving. So I would love to have some help understanding that, but so it's a very interesting result. And we have some interesting results, frankly, with the core shell systems too. As a function of, I'm trying to think, as a function of the shell thickness, we're seeing that the energy, so what we're seeing electrochemically is that the gap is not really changing, but that both the valence and conduction bands go down in energy and then up again as we increase the shell thickness. And these are brand new results, and we're trying to understand why, why that's happening. So if you have any ideas, on the chat. But so a couple of interesting results. Yeah. But as you know, maybe, so a lot of the energy level diagrams are produced from thin films or from bulk materials, and not so much from the nanomaterials. So there's much less literature that really helps us pinpoint the actual, band levels. So what I show is not necessarily super accurate. Yeah.
Quick question on something different than what you were showing on explosive growth of ELS.
Uh-huh.
Do you see the density of growth change also? I mean,
Yeah.
those two,
So there does seem to be an induction period, and so so basically there's a period of time where things aren't really growing that well. So basically it's the time you're adding precursor into the flux. Is what we think, and then the particles will take off, but some do, some don't, and that gives rise to some of the variability we see in terms of lengths, because some of the particles have taken off earlier than others, and so they're
So the catalysts are staying the same size. You don't see some sort of ripening effect of the catalyst, so it gets to a critical size before the growth starts to take off.
No, we definitely see some. That's the induction time. I mean, so that, and then we also see, where is it? No. So in the case of so you can see that the alloy interface the alloy region is often fatter than the pure phase regions, and I assume that's just because we've swollen the catalyst with the other phase. It seems to happen quite a bit, yeah. Not constantly, but so, yeah.
So it's not just a lattice change that's causing that. It's actually a catalyst.
I think so. We don't have definitive proof, but yeah. So, any questions?
Maybe this is actually a perfect slide.
Okay.
So in this alloy interface,
Yeah.
is that I mean, from my guess perspective, do you see some twinning in that area? Is that
Yeah. So I should have brought. I didn't bring this data. Okay. So the CAD selenide is growing wurtzite, the zinc selenide cubic. And so they're meeting, it's a quasi, my TM expert is calling it quasi-epitaxial at the interface.
Correct.
So they're meeting at the lowest energy possible interface that they can. And so, yeah, I mean, that's...
Right. So I guess my question is that a truly alloy interface and essentially a combination of the quantum dots, almost like two-dimensional sections?
I don't
which
know.
Would be very interesting in its own right, but
Honestly, I don't know. I don't know. Yeah. That would be interesting. Yeah.
right.
Yeah.
And maybe one more question that came to mind when you looked at the suppression of blinking.
Yes.
In I don't know where
Well,
I guess what I'm interested in your suppressed picture.
Yeah.
It doesn't seem that you ever decay the photoluminescence completely.
You mean the indium phosphide.
Right.
Okay, this is all brand new data, by the way. So
Okay.
we're still trying to figure it out.
So just what I'm
Yeah.
trying to figure out,
Yeah.
maybe, I guess,
Yeah.
is how much of this, especially in the second graph, can you actually really associate with blinking rather than potentially noise or other effects in the data? I would think that you would go essentially die off completely, but it doesn't seem like it's happening all the way.
Right. So I mean, actually, in the top graph, it is happening all the way.
I agree.
Yeah.
I agree. That's
So,
probably really fast, but
and so in the bottom graph, it's not because it's we're not actually losing the emission. I mean, the intensity is never dying away. And sorry, I mean, again, this is not, this is, I work with Han Toon and his postdocs, but they clearly take into account noise in the measurements. So we had to deal with that ages ago with the other system, but yeah.
You basically have almost like no blinking in that case.
Yeah. No, I know, and that's what's exciting. So the sort of the dirty secret behind these guys is that because this is actually a truly, we think, a real type 2 system, largely because the lifetimes are very long, a few hundred nanoseconds. I mean, very, very long. And the dramatic, so we're getting this very dramatic red shifting of the emission maximum out into the infrared beyond the bulk band gap of indium phosphide. I mean, you got clearly a CT kind of state going on. And so, so that makes these fairly dim. The quantum yields are not awesome for this system, but which is why it's such a torture to get this data. but anyway, it's still interesting. So we're looking at the in-between shell thicknesses where we still have fairly bright dots, but we're thinking we'll probably see some suppression of blinking there too. So trying to find that happy medium. But that's not noise. So.
I've got a follow-on question.
Yeah.
They look quite well behaved in their blinking.
I know, and this is why this is uncharacteristic. This is not your standard blinking behavior that you see from dyes or anything.
You talked about gated techniques, time gating techniques.
Oh, okay.
Things out of the noise.
Yeah.
One of the standard techniques is a lock-in technique, which we all know about. But when you get down to the noise levels on things like that, and even with the big Stokes shift you've got, a lot of your noise, at least in my systems, most of the noise comes from excitation light that leaks through. And so it's really tempting all the time to say, oh, well, let's just use a lock-in technique. But it doesn't work when you're trying to blink your very source of all your noise. So if you decouple those, you can really improve your signal to noise, typically by orders of magnitude. But, if you turn your laser off, you turn off your signal. But you can get it to blink without. Now, if you can get them to blink characteristically, sorry, I'm doing a terrible job. Sleep deprivation, sick kid. Anyway.
I understand. I'm not trying.
The characteristic frequency, and it doesn't have to be locked.
Okay, that still would be interesting.
Like 100 hertz
okay.
or whatever.
Yeah.
And just keep the laser on, and then look for a signal in the noise. Right.
With that characteristic frequency.
And you should be able to pull it up by an order of
that would be interesting. Yeah, and okay.
I'd like to hear if it works.
So you've just come up with a new application for the one.
I'm really curious.
So I'll tell you another secret. So then my chemist went back and made another batch of the 4 shell, and they look more like normal blinkers. They go off with longer off times and more random off times. So we'll have to figure out what she did here, what she did there.
You're getting the lead for some control.
Yes.
With the settings.
Yeah, exactly. No, that's why this system turned out to be more interesting than we expected, because it's. But yeah.
Well, I'm very curious. I'd like to hear
Okay. Sounds good. Thanks.
Thank you.
All right.
Any other questions for Dr. Colloidal? Jonathan?
Yeah.
So I'm just, if you could comment a little bit further. So from your results, I guess the conclusion on the suppression of blinking, would it be fair to say that this thick shell just prevents the core from spurious charging?
That's certainly an aspect. So it's actually a second paper that's now in submission. Well, so the paper I referred to that's coming out in Nature actually, we limited to, I think, 7 shells. So I wasn't explicitly looking at the giant dots. We kept 7 because they were stable enough to do this technique, the spectroelectrochemistry technique, but we still had blinking, behavior to look at. And so I'm trying to remember now. Okay, so when we go from 7 shells to say 16, which is our non-blinking, nominally non-blinking and that kind of range, I'm trying to think. I'm pretty sure there was a transition. So you've got this we call A and B type blinking. So 2 different sources. One, you've actually got charging, and then the other, you just got this magic, carrier trapping to a surface state and that pops back in, and no change in lifetime, so forth. And I think our conclusion is that latter scenario, that carrier trapping, so not actually charging, is at least in the ones that we've looked at in that middle shell regime, is the dominant mechanism. So as opposed to the charging mechanism is real, it exists, and it's certainly valid. There's been recent debate in literature as to whether that mechanism is at all real. And it is, but it seems to be less, less of a driver.
Unless there's any other questions, I have a few closing comments. Maybe I'll just say that one of the reasons that Dr. Hollingsworth is here from Los Alamos is the chief scientist of her organization, the chief scientist of CIN, the Center for Integrated Nanotechnologies at Los Alamos, is in fact on our International Scientific Advisory Board. So this was the initial connection. And Dr. Carty and I went down there in March.
March, I think, yeah.
Maybe we had seen you, and we looked at their organization and the complementarity of the research, and we agreed that to strengthen that, we'd bring strong researchers into a mobility sort of exchange program to start. So this was the first, I guess, exchange. We'll probably be sending someone from WIN down there to do something similar. It's very likely could be in energy or fabrication, and it's actually interesting. This has been the best part of this possibly, has been this discussion at the end, because I couldn't help but count about 10 WIN faculty members that showed up today, and I can see a few nanotechnology graduate students here as well, so the right kind of group as well. So with that being said, that was a fantastic talk. Thank you very much.
Well, thank you, and I really appreciate the opportunity. Yeah, thank you.
Thank you.
Thanks.